In 1956, Noam Chomsky asked a question no one had answered before. What kind of thing is a language, mathematically? His answer: there are exactly 4 types, each strictly more powerful than the last, each corresponding to a specific kind of computer that can recognize it. It's called the Chomsky hierarchy, and it's one of the deepest ideas in computer science. Where a language sits in the hierarchy tells you what your computer can even in principle recognize. And spoiler, natural human language sits above the level any classical parser can handle, which is a big part of why NLP is hard. Last video I promised you a math toolkit that isn't scary. Today we start using it. Chomsky's hierarchy is the first big idea, and it is a great warm-up because the math is mostly about categories. This class of language, that class of machine. Not calculus, not measure theory, just careful naming and nesting. The puzzle. If a language is a set of allowed strings, what kinds of sets are there? What kinds of rules generate what kinds of sets? What machine can decide is this string in the language? The 4 answers Chomsky gave to those questions form the hierarchy, and each answer sits on a strict rung above the one below it. Today's 3 beats. First, the 4 types: regular, context-free, context-sensitive, recursively enumerable, nested, strict. Second, the machines. Each type of language pairs with a specific computer: FSM, Pushdown Automaton, linear-bounded Turing Machine. Third, where natural language actually sits. Spoiler, not comfortably in any one type, which is the whole story of syntax for the last 60 years. Beat 1. Type 3. Regular languages, the simplest. A regular grammar has rules like start symbol goes to a terminal followed by another non-terminal. That is, it's a straight line pattern. Examples: phone number formats, email addresses, anything you'd write as a regular expression, simple, fast, common. Type 2. Context-free languages, one step up. Rules like start symbol goes to any string of terminals and non-terminals. You can nest things, which means you can describe balanced parentheses, programming languages, and most of what people mean by a grammar in linguistics. The Penn Tree Bank uses context-free grammars. Every parser you've heard of computes them. Type 1. Context-sensitive, even more expressive. Rules can depend on the surrounding context, hence the name. Certain natural language phenomena live at this level. Type 0. Recursively enumerable. Anything a Turing machine can recognize. That's every possible language. Everything computable. Full stop. Beat 2. The machines. Every level of language pairs with a specific type of computer. Regular languages pair with finite state machines. FSMs are the workhorses. Small memory, fixed number of states. If a language is regular, an FSM can decide is this string valid. Fast, constant time per character. Context-free languages pair with pushdown automata. Add a stack to the FSM and you can handle nesting. Push a symbol when you open a parenthesis. Pop when you close. Programming language parsers work this way. So do most classical NLP parsers. Type 1 pairs with linear-bounded automata. Type 0 pairs with Turing machines. The important thing about this pairing, it means the 4 language types are ordered by computational power. Higher up the ladder, more expressive language, more powerful computer required. Nothing is universal. Everything has a price. Beat 3. Where does natural language sit? If English were context-free, type 2, you could parse it perfectly with a pushdown automaton. Cheap, fast, solved. But English is not context-free. There are specific constructions, like Swiss-German cross-serial dependencies, that require more than a context-free grammar. They live above type 2. But natural language is also not full-on type 1. It sits somewhere in between. Linguists call this region mildly context-sensitive, and there are formalisms designed specifically to fit: tree adjoining grammar, combinatory categorial grammar. These are type 1.5, roughly, efficient enough to compute, powerful enough to handle real language. So here's the big picture. Chomsky's hierarchy is a math statement about possibility. Where natural language sits tells you which classical machines cannot handle it. That is one reason NLP moved to statistical and neural approaches. Not because grammars are wrong, because natural language is too expressive to be captured by the machines that grammars pair with. 3 takeaways before the quiz. 1. 4 types: regular, context-free, context-sensitive, recursively enumerable, nested, strict. 2. Each type pairs with a specific machine: FSM, Pushdown, linear bounded, Turing. 3. Natural language lives above context-free, below full context-sensitive, mildly context-sensitive. That's why classical grammars can't fully do it. Quiz 1. Which grammar type can describe balanced parentheses like double open A, close B, close close, irregular type 3, B, context-free type 2, C, only Turing complete grammars, or D, no grammar can describe them? B, context-free, because balanced parentheses need arbitrary nesting depth. A regular grammar can't remember how deep you've gone. A context-free grammar can. That's exactly what Pushdown Automata add with their stack. Quiz 2. Which machine matches which grammar type? A FSM matches type O, B Turing matches type 3, C Pushdown matches type 2, and FSM matches type 3, or D, they all match everything? C. Pushdown to type 2, FSM to type 3. Simpler machines match simpler grammars. To go higher, type 1 needs linear bounded automata, type 0 needs full Turing machines. It's a strict ladder up in both computing power and grammar expressiveness. Quiz 3. Where does natural language sit in the Chomsky hierarchy? Irregular, B, context-free, C, mildly context-sensitive, above type 2 below, full type 1, or D, full recursively enumerable? C. Mildly context-sensitive. Formalisms like tree-adjoining grammar and combinatory categorial grammar sit here, specifically designed to be more expressive than context-free, because of things like Swiss-German cross-serial dependencies, but still efficient to parse. Back to the puzzle. Chomsky gave us a map. The hierarchy tells you what kind of language you're dealing with, and which computer can even recognize it. And even though modern NLP mostly bypassed the strict grammar machine pairing with neural networks, the hierarchy is still the ground truth of what's computable. Next video, the workhorse machine of the whole map: finite state machines. Next time, finite state machines. That dropdown that auto-completes your address? FSM. Your spell checker? FSM. Finnish phonological analyzer? FSM. Boring? Maybe. Everywhere? Definitely. Hit subscribe.